Hello, everyone. Welcome back to the second session of the BPS today. And we have now Hariharan Narayanan from TIFR Mumbai, and he'll be talking about large deviations for random hives and the spectrum of the sum of two random matrices. Very curious choice of the places of the. So, Hari, yeah.
Yeah. So thank you to the organizers of the Bangalore Property Seminar for this invitation. It's a pleasure to speak here. So I started explaining what hives are. So hives are certain combinatorial gadgets introduced by Knudsen and Tao for the solution of something called the saturation conjecture in about Littlewood-Richardson coefficients in representation theory. However, there are also some interesting connections with random matrices, and this talk is going to leverage on those connections to get some large deviation estimates for the spectrum of the sum of two random matrices, as well as for the hives themselves. So here, what you see before you is a hive. It's a triangular array of numbers. So you write the numbers on an equilateral triangle, the interstices or vertices of an triangular grid of this sort. On all the sides, if you do a piecewise linear interpolation of the numbers, then you get a concave function. So here, for example, you see 0, then 40. So the slope here is 40. Between 40 and 70, the slope goes down to 30. Between 70 and 90, the slope goes down to 20. Between 90 to 100, the slope goes down to 10. So, sorry. So this is a concave function on this line. Similarly, if you do the piecewise linear extensions for the other three sides, you will find that they are concave functions. So a hive is a way of extending this to the interior in a way that the resulting function is piecewise, continues to be piecewise concave. And in the discrete sense, if you look at all the vertices at the unit rhombi, they have to satisfy the condition that the sum of the entries on the larger diagonal have to be greater or equal to the sum of the entries on the smaller diagonal. So if you check this for example, if you check this rhombus, you see that the sum of the entries in the longer diagonal is 100, and the sum of the entries on the shorter diagonal is 105. So I don't remember what I said, but what I wanted to say was that the sum of the entries on the longer diagonal is less or equal to the sum of the entries on the shorter diagonal. I may have said it the other way, but this is what should be the case. So they have to kind of if you take a piecewise linear extension of this hive to the interior of the triangle, you should get a concave function. Okay, so this is what a hive is, and we will call by the discrete Hessian the function that goes from unit rhombi to reals, which takes a particular rhombus to the value d plus b minus a minus c in a figure like this. So it's the sum of the entries on the longer diagonal minus the sum of the entries in the smaller diagonal. Concave functions have Hessians that are non-positive definite. So as a reflection of that fact, we want to say that the discrete Hessian is non-positive for this discrete concave function. So that is true. So here is the connection with representation theory. So the so-called irreducible representations of GL and C are indexed by partitions. So these are basically what happens when you have this Lie group acting on a vector space, and you break up that vector space into a direct sum decomposition of irreducible representation. And then what this is saying is that if you take the tensor product of two of these irreducible representations and then break that up into irreducible representations, the multiplicity of seeing a particular partition nu in the tensor product of V lambda tensor V nu is this Littlewood-Richardson coefficient C lambda mu nu. And that number is actually the number of integer points in a hive polytope. What does that mean? It means if you fix the boundary given by lambda mu and mu, It's the number of ways of extending to the interior vertices with interior vertices with interior values in such a way that all these rhombus inequalities are satisfied. So if you just look at all the inequalities that are defined by these rhombi, they form a polytope. And this number is the number of integer points in that polytope. So this is the connection to representation here. Here I've reiterated this. This is just for background because this was the original setup in which this hive model of was invented by Knudsen and Tao. So I wanted to give this for background, but it will not be required in the rest of the talk. Our motivation is more statistical. It comes from random tilings and study of random matrices and so on. So these hives are in one-to-one correspondence with pictures like this called honeycombs. In fact, this more Knudsen and Tao's original paper was mostly in terms of honeycombs. But it turns out that hives are an equivalent description of these objects. The way the correspondence goes is that if you look at a picture like this in R2, you look at the correspondence, and there's a way of assigning to it a hive, where what you do is you look at this point and say that this is going to be the gradient of the hive at this vertex, at this triangle. So this triangle is piecewise linear, the small triangle, and it has a single gradient. And you say that that is equal to the position here. Similarly, the vector here is the gradient at the triangle below it, and so on. And why should such a picture then emerge? Because it will emerge because if you look at the difference between the gradients of a hive or two such piecewise linear triangles, it will have to be orthogonal to the side common to the two triangles, because on the side common, these two piecewise linear functions agree. So if you look at the difference between this function here and this function here, these two linear functions, it's going to be 0 here. And that's why the gradient of that linear function, which is 0 here, will have to be perpendicular. And that is why you see this kind of a picture. These lines are either always in this direction vertical, and these angles are always 120 degrees. Okay, so this is what a honeycomb is. These semi-infinite lines are in correspondence with the points lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, which are the successive differences of the entries on the hive on the boundary. So here, for example, the successive difference is 40, the successive difference is 30, the successive difference is 20, the successive difference is 10. That is what these things are. So are there any questions so far about hives or honeycombs?
It is not clear if there is at least one extension, right?
No, it is not clear if there is at least one extension. It is not clear. In fact, it is not always true.
Oh, okay. Thank you.
Yeah, sorry, I had a question.
Yeah.
Yeah, this is regarding this parallelogram pattern that you showed. The fact that, the longer diagonal and shorter diagonal, you're kind of comparing cross values, right? Not sort of adjacent values.
No. So the inequality says y plus w is greater or equal to x plus z.
Yeah, this kind of monotonicity, for some reason, it doesn't remind me of concavity. It looks more like some kind of mixed partial being greater than equal to 0.
That's true. That is true. This is a stronger condition than just concavity in general. But for these lattices, it turns out that if you have a piecewise linear extension that is concave, because of the positions of the vertices, it is equivalent. So concavity of this piecewise linear surface and rhombus concavity, which is that this condition, that this plus and so on, those turn out to be equivalent.
I see. Okay.
Yeah.
Right.
So in general, if you have a smooth function and you say that these mixed partials are positive or negative, as the case may be, then that is a stronger condition than saying that along each line the second derivative is negative or non-positive, which is what plane convexity would tell you or concavity would tell you. So here they also come up in square triangle tilings. So these Littlewood-Richardson coefficients, which count the number of integral hives, they are also equal to the number of tilings of certain domains using squares and equilateral triangles. So you see this domain is now chalked out by the green pieces, which are not part of the domain. And this is the domain has been filled by purple, white, and red. So this is some kind of tiling of this domain. And what happens is this becomes in correspondence with a thickened honeycomb. So you look at this picture, what you see is a thickened honeycomb where all the lines have been thickened by squares, all the vertices have been replaced by equilateral triangles like this. And so this picture is a discrete honeycomb really. And as you see, if we just had filled the interiors of these hexagons using only equilateral triangles, which can be done, then you will get a tiling of this picture involving squares and equilateral triangles, but it will also be in correspondence with a discrete honeycomb and hence with a discrete hive. So these are all equivalent, they're combinatorially equivalent. And here I've just given, for those of you who know the Young tableau interpretation of Littlewood-Richardson coefficients, here this is called as Q Young tableau. You have 1s, 2s, 3s written in monotonically increasing order on the rows and strictly decreasing columns. But there is one extra condition called the LR condition, which is that if you read it from right to left, bottom to top, 1, 1, 1, 1, 1, you see, then you see 2, 2, 2, 1, 1, 1, etc. 1, 1, then 3, 3, 2, 2, 1, 1, then 4, 4, 3, 2, 2, 1, 1. So this sequence has the property that at any time, the number of 1s encountered is greater or equal to the number of 2s encountered, is greater or equal to the number of 3s encountered, and so on. And that you will see is true for this sequence. Okay, and as you see, this has been color coded to this. So this picture was taken from a paper of Kevin Kurbu called Puzzles, Tableau, and Mosaics. But this correspondence between this Q Young tableau, which satisfies the LR conditions, are called LR's Q tableau, and these discrete honeycombs in this proof by picture is due to Terence-Tao. It is attributed in that paper to Terence-Tao. So here all the reds go to red here. These two ones go to these two ones. These two ones go to these two ones. These two ones go to these two. And the twos go here from here to here. So they're color coded in this fashion. So you can see the correspondence. So they're equivalent encodings of the same quantity. So this is this idea of studying tilings by associating a height function is something that is done in this field. So, for example, for Lorentz tiling, this is a picture courtesy of Petrov. What one does is you have this sawtooth domain where in the top you have you should see a little sawtooth here, and it's flat from here to here, sawtooth here to here, flat here, sawtooth here. And we are trying to tile using three kinds of tiles: rhombus tilings that are vertical, which are I guess blue-green; rhombus tilings which are sideways, which are orange; and rhombus tilings that are sideways in the other way, they are red. But if you look at this from far away, it gives you the sense of a three-dimensional picture. The reason is that, well, the reason is somehow visual, but the point is that you look here, you see this flat wall in one direction, you have see this flat wall in another direction, and this you can think of as the floor. At least this is the way I see it. And you see that here you have a surface of some sort across this corner. So you can take this tiling and you can assign numbers based on this heuristic visual idea to get a height function on the nodes on the vertices of this lattice. And that you can now study that function and its limit, shape, etc., instead of studying the tilings directly. So similar idea can be used to study those hexagonal tilings corresponding to honeycombs or the square triangle tilings that corresponded to integral hives by studying the integral hives random structure and limit shapes if possible and so on. So this is a general principle in studying tiling to study the height function instead. But now I want to talk about the connection to random matrices, since that's the going to be most of the focus of this talk. Not only are the number of integer points in these hive polytopes representing a literal decision coefficient, which are interesting quantities in representation theory, but the volumes of these hive polytopes, that is their Lebesgue measure, with a scaling term, which I'll explain briefly, give you the probability density of obtaining a particular Hermitian spectrum from the sum of two random Hermitians with given spectra. So this is a basic problem which in fact has been studied as early as by Hermann Weyl, and this gives an explicit description of what is the density of the spectrum, or I should say, yeah, the spectrum of the sum of two random matrices. So here I'm going to now spend a lot of time in this picture. So we are now considering the question of two random matrices, X and Y. The first one has spectrum 15, 5, minus 15. You see that there are successive differences in the vertical here. And the second matrix has the same spectrum, 15, 5, minus 15. We are going to conjugate these two diagonal matrices with these eigenvalues with independent unitary matrices from the Haar measure, that is from the unitary group. And then we are going to take their sum. And then we are going to ask what is the probability density of the spectrum of the sum of these two matrices. And it turns out that the answer to that is encoded in this pink diagram. So here is what we are going to do. We are going to now create this. We call this picture an augmented hive. What you see on top here is going to be a hive in the sense that we discussed earlier, except that it's been distorted to make it a right triangle, isosceles right triangle. Earlier it was an equilateral triangle. This part below here is not a hive because the squares here do not satisfy the rhombus inequality. So here, for example, it is not true that the sum of the entries on this sum, that is 10 plus 15, is greater or equal to 20 plus 7, because 25 is less than 27, not more. So in fact, that particular inequality can be violated. So what you see here is a kind of decoration on the hive. So here is a hive on top. On the bottom is actually a so-called Gelfand-Setlin pattern, which is drawn in red here. So the successive differences on the diagonal form a pattern called the Gelfand-Setlin pattern, which is also studied in representation theory. But it's in fact closely related to Lorentz tilings as well. And the important thing for us is that the volume of the corresponding polytope of Gelfand-Setlin patterns is equal to a van der Waals determinant. So if you see in the previous slide, we said you have to take the volume of these hive polytopes, multiply them by certain van der Waals determinants. By putting this piece over here, I'm essentially scaling up the volume of this hive polytope by a van der Waals determinant to give us exactly what we need. So if you now look at this picture, this square, what are the constraints? The constraints are on the upper triangle. You have all the rhombus inequalities. Namely, if you take a parallelogram like this, it should satisfy the rhombus inequality that this plus this is greater or equal to this plus this. Same is true for the squares. Okay, you think they're distorted squares because the equilateral triangle has been distorted to a right triangle, but this is, you should think of this as a rhombus in terms of the previous picture. And also the rhombi of this sort that I'm outlining now. In all of these, the sum of the entries of the marked diagonal has to be greater or equal to the sum of the entries of the unmarked diagonal. That is true in this upper triangle because that is a hive. In the lower triangular, the other two inequalities for rhombi of this sort and rhombi of the other sort, namely this sort, they have to hold, but they don't have to hold for the squares. The squares don't have to satisfy the rhombus inequality. So these in some sense correspond to Gelfand-Sutton pattern. So are there any questions regarding what are the constraints satisfied by these augmented hives? Okay. So now I want to give you the punchline. The punchline is, in order to get the spectrum of the sum of two random matrices with the spectra I mentioned, 15, 5, 5, minus 5, minus 5, minus 15, and 15, 5, minus 5, minus 15, it suffices to pick a random point from this polytope. The bottom side incidentally has to be set to 0. The bottom side is set to 0. You pick a random point from this polytope and load the values on this pink diagonal. So in this case, again, we have just got 0, 15, 20, 15, and 0. And then take the successive differences, 15, 5, minus 5, minus 15. This is a vector in decreasing order or non-increasing order. And the distribution of this vector is exactly the same as the distribution of the spectrum of the sum of two random matrices, X and Y, where X and Y are randomly conjugated matrices with the spectra as specified here using independent unitaries. So this is the main theorem of, this is one of the main consequences of this work of Knudsen and Tau. This is a very interesting relation of how the sum of two random matrices spectra get related to some explicit polytope. So what we want to do is we want to take this explicit polytope and let the side length, these mesh lengths tend to 0, and then look at the large deviations of the related surfaces and of these random concave functions that we get on the pink diagonal, because that tells us about the spectrum of the sum. But we are also interested in the entire hive as a whole simply because of its geometric relevance and its and I mean, it seems like a central object to study, not just the spectrum of the sum, but also the geometric shape. So in order to define the large deviation principle for the spectrum of the sum of two independent random matrices, we have to first come up with an embedding of these probability spaces with corresponding to the spectra of xn as n tends to infinity. So we have to tie them all together first. So and then we have to embed all of those probability measures into L infinity 0 in some nice way. The way we are going to embed them into L infinity 0 is simply by taking the piecewise linear concave function and looking at that piecewise linear concave function on this pink diagonal as a subset of L infinity 0, 1. So that is how it is embedded. But how are all the Pn related? All the Pn are related by we are going to fix some fixed concave functions on the vertical side of the square. Here there's going to be a strongly concave function. Here another strongly concave function, and these things are going to be the slopes. The lambdas are in some sense going to be the slope of this concave function, which is monotonically decreasing. In fact, strictly decreasing because we are talking strongly concave functions. Okay, so here is a setup. Lambda mu are strongly decreasing, bounded on 0, 1, integrate to 0. That is to reflect the fact that when you take the integral, you get 0 at the endpoints. Lambda n of I, which was the ith eigenvalue of lambda n. Lambda n is a sequence of n eigenvalues. I is the ith element in that sequence. is going to be n times the integral of lambda from I minus 1 by n to I by n. Okay, so it's a discretization of lambda. Lambda n I gives you this. Mu n of I is similarly n times integral I minus 1 to n by n to I by n of mu. Sigma of S is a quantity known as the surface tension, which I will define clearly later. For now, I will just say that it is the negative of the logarithm of some function of the average Hessian S. Okay, local in some sense. So let me not go into great detail now. I just want to say that at every point of a smooth hive, there are three numbers that come from the limit of a discrete Hessian as the mesh tends to 0. So this is going to be a function, a certain function of those three numbers. Okay, this is we take S to be positive, so it's the negative of the Hessian. And V lambda is some continuous analog of van der Waals determinant. So this e raised to integral of log lambda x minus lambda y by x minus y is an analog of some scaled van der Waals determinant in the infinite limit as the scaling tends to 0. So this is going to be the so-called rate function we look at. The rate function corresponding to gamma, which is a concave function on the pink diagonal, is the logarithm of this v lambda v nu by v nu v tau. Tau is some standard parabola with the Hessian, which is a constant, plus the infimum over all continuum hives with boundary values lambda, mu, and mu. What do we mean by continuum hives? We mean that these are now something which is a real value function in the entire triangle, not just on the lattice points. And for every rhombus or square in the deformed case, the corresponding inequality involving 4 numbers has to hold, not just for the lattice triangles, for every not just for the lattice parallelograms or rhombi, but for every parallelogram of every side length. Okay, and what are we integrating? We're integrating the surface tension, which is some function of the negative Hessian, the absolute continuous part. So now in this, we are not requiring H to be smooth. H can be a Lipschitz concave function. When you have a Lipschitz concave function, you can take its, you can define its Hessian, which would end up being a radon measure, which is a measure that satisfies some inner and outer regularity, such that it will have an absolutely continuous part, which is absolutely continuous with the Lebesgue measure, and a singular part, which will separately be there, but it will not matter in the expression. So that singular part will vanish as far as the effect on integral of sigma is concerned. Okay, so this is some functional on gamma, and it will come up in the large deviation theorem. So I'll say this and then I'll pause for questions. So what is the theorem? The theorem is saying that suppose I want to know for some fixed Borel subset of L infinity 0, 1, what is log of Pn of E in the limit? So I need to rescale it by An inverse, where An is n squared by 2 to get something sensible. But An inverse log Pn of E as n tends to infinity, its lim inf and its lim sup are bounded above and below by the supremum of minus I gamma over the closure of E and the supremum of minus I gamma over the interior of E. So this is the large deviation theorem. Large deviation theorem typically have this form, so we also have the standard form. Except that I should have told you. So no, so there is some issue about what is the topology. The topology is not the L infinity topology for us. We look at the, let's see. So we'll come to that. I mean, it's depending on whether you're looking at lambda or you're looking at the function values, you have to talk about two different things. But essentially, we are talking about it is in L infinity. The large deviation estimate is in L infinity, the way I've stated right now. So, are there any questions so far?
Is it obvious that the integral exists in the previous slide? Yeah. This infimum of over little h of integral.
Yeah.
Okay. Now, it is quite positive. Oh, I see. Is it positive? No, it may take positive and negative values, right? Integrand.
Yes. Yes.
Therefore, integral of positive part and negative part at this moment could both be infinity.
Yes, that is true. But so what happens is, so this is somehow the logarithm of the most likely surface.
Right.
So most likely surface. So if you have a good surface, so as you earlier pointed out, you don't even need to have an extension.
Okay.
But if you have an extension which furthermore is nice in the sense that all the Hessians are bounded away from zero everywhere, then this will be some finite number.
I see. Okay.
I had a question about the definition of PN.
Yeah.
So PN is what you take those spectrum of xn plus yn and then linearly extend those functions, and PN is on those functions. Is that correct?
No, say that again. I missed you. Definition of
PN.
PN. Yeah. So PN is basically comes from the probability distribution of the nth approximation of the question. So what is the nth approximation of the question? You define lambda n of I in this fashion. So lambda and mu are what are given. These are strongly decreasing, bounded on 0, 1, integrate to 0. The nth approximation of the question is this thing where you have n numbers obtained in this fashion from lambda and mu. Once you have these n numbers, then you can talk about, okay, let's take these two finite dimensional matrices which are random, add them and look at their spectrum. That has a certain probability distribution, the spectrum of the sum. And that distribution is getting encoded as a concave function in L infinity 0, 1 by taking the slope. So
I see. Okay. Yeah, no idea.
Yeah.
That's good. So is this telling you the cost of deviating from
yeah.
So from the okay.
Yeah, so it is telling you, so if you fix a Borel set E, it's telling you at what rate does the probability that you fall in that set tend to 0. It will always tend to 0 unless you contain some special, generally, like for example, for Gaussian matrices, you have a semicircle law. So if you take a box around the semicircle law, you are always going to have a set of large measure. When you take a logarithm, you will still get something that is not going to infinity. But if you take any sort of atypical set, then the probability that the spectrum concave function lies in that set, that will go to 0. But if you rescale it by this 2 by n squared, you can still make sense of that number, and it will be given by these things.
In the previous slide, you mentioned earlier that you will say something about the f, the function f.
Yeah, I'm coming to it. This is the next slide, in fact.
I see. Okay, all right.
So the point is, f is basically the entropy contained in a quadratic concave function per vertex when you have Hessians of prescribed values. So if for example in this kind of rhombus the Hessian is minus S0, this kind of rhombus the Hessian is minus S1, this kind of rhombus the Hessian is minus S2 on average. So it's some kind of random surface with this average Hessian. and this measures the entropy. So now this is the idea. So let me make it more precise. So what are we going to do now? We're instead of working with this on average idea, we're going to say that okay, let's look at periodic Hessian surfaces on some with a very large period. So this is some very large period, and we are looking at periodic Hessian surfaces, and the total Hessian on all of these rhombi in this big parallelogram or rhombus is going to be n squared times S0. Okay. In this direction, what does that mean? It means basically that okay, so let me not go into further detail. So you get the point. So so we're going to, instead of looking at, we want to understand what is the entropy per vertex of quadratic surfaces with given Hessian on average. Instead, what we're going to do is we're going to say that okay, let's get this to be the average Hessian exactly on periodic Hessian surfaces. Now, periodic Hessian means the average is very well defined because you just look at a fundamental domain and you know what the average. There's no infinity in the picture. You look at a fundamental domain, you look at the average Hessian and you know what the average Hessian is. But this is again, it's like a big thing, right? On the full plane, because it's going to look like a paraboloid. We don't want to look at a full plane, we want to look at a torus with this as a fundamental domain. So what we do is we add to this random paraboloid a fixed paraboloid which is convex as opposed to concave, with the Hessian S0, S1, S2 on these rhombi, the same rhombi. Recall that I said for the random Hessian, it's going to be approximately minus S0 on this. For the thing we are adding, it's going to be plus S0. It's a deterministic quantity we are adding. So what was earlier a random paraboloid with concave, this thing, which is concave, has now become a periodic semi-concave function, meaning the Hessians everywhere are dominated by S0, S1, S2 on the rhombi of particular kind. So periodic semi-concave function, but it is now a periodic function. So you don't have to look at it on the whole plane. You can just look at it on a fundamental domain or on a torus. Okay, so the entropy is going to be defined in terms of the volumes of these polytopes. These will turn out to be polytopes of mean zero function. You can of course add a constant. So we don't care about that. So we're going to impose a mean zero condition and look at the volume of these polytopes, raise it to 1 by n squared, and prove that a limit exists as n tends to infinity, and that will be our f of s. Okay, so it's a slightly roundabout definition, but this is the way it is roughly speaking done by Cole, Kenyon, Prof when they study domino tilings and lozenge tilings. So this is like a standard practice model in this field. So you define the surface tension in this fashion for the periodic case, and then you use that with some additional arguments in the non-periodic case. So so this is now I'm going to talk about some ideas involved in proving that the limit of Pn of s to the 1 by n squared exists as n tends to infinity. So are there any questions about the definition of Pn of s? Okay. So let's suppose s is equal to S0, S1, S2, and the 2 is equal to S0, less or equal to S1, less or equal to S2. So we see that any mean zero function on the discrete torus taking values in minus half half belongs to Pn of s, which therefore contains the central section of the unit cube. By a result of J. Waller, any central section of the unit cube has a volume of at least 1. Therefore, Pn of s is greater or equal to 1. Okay, so this is kind of a lower bound, which is a priori a lower bound. Then we also get a upper bound using differential entropy and some ideas involving the Pfeffer-Lindner inequality and differential entropy of these things. So this gives a upper bound of 2e. And then once we have the lower bound and the upper bound, we also prove some kind of approximate monotonicity, which is not true like everywhere, but in almost everywhere it is true. And roughly speaking, and that is sufficient to prove that the limit exists. So this is some very technical part which I'm not going to go into greater detail, but it involves breaking up a big torus into small tori and doing things like fixing the boundary to get a lower bound on the volume of the big tori in terms of the smaller tori and things like that. So some similar ideas we will see anyway later in the non-periodic case, but those similar ideas are there here also. So now for the rest of the talk, so incidentally, did we start at 20 past?
That is correct.
Okay, thanks. So so the main tools involved in this are actually tools from convex geometry, because those polytopes involved play a heavy role. And so I have to describe some basic inequalities that we use repeatedly. So one is the Brun-Minkowski inequality. What does the Brun-Minkowski inequality say? It says that if you have two compact convex subsets of Rm, where m is greater or equal to 1, then the volume of K plus L to the 1 by m, where m is the dimension of both of these bodies, is greater or equal to the volume of K raised to 1 by m plus the volume of L raised to 1 by m. Now, what do we mean by the Minkowski sum of two convex sets? So here is one convex set, the blue convex set. Here is one convex set, the green convex set, which is partly occluded. But nonetheless, this whole body that you see overall is the Minkowski sum of the blue convex set and the green convex set. So the way you obtain this big body is you pick up, it's the set of all vectors which can be expressed as the sum of two vectors. The first inside the blue body and the second inside some central green body. So these should be thought of as translates of some central green body to the some various points. So you basically use you kind of map out a larger domain by moving these green bodies with their centers, so to speak, occupying arbitrary positions in the blue body. So you think of this, if these had been balls, for example, these green bodies had been balls, you take the center and you move that center everywhere in the green body, and you see what kind of a body gets mapped out, covered by this movement. That is the Minkowski. So this gives an lower bound on the volume of this Minkowski sum in terms of the volume of the bodies. And in fact, if you have two parallel bodies and you look at the convex hull, so parallel two-dimensional bodies in 3 dimensions, for example, as in the picture here. Here you have two parallel two-dimensional triangles, and you're looking at their convex hull in 3 dimensions. Then you can take these sections at intermediate points, and those sections will contain the Minkowski average of these two sides, where the average is a weighted average with respect to this distance is to this distance. So if it's exactly at the midpoint, then it is halfway. Otherwise, it's closer to here, you'll get a weight of 2 on this and 1 on this and so on. So because of this, if you look at the volumes of these sections, they are all concave functions because they are because of this Brun-Minkowski inequality. And so the same idea tells us that Fn of S must be a concave function, because these Fn of S can actually be thought of as sections of some higher dimensional convex cone. And then by the Brun-Minkowski inequality, it turns out that this will be a concave function. Pn of S to the 1 by n squared minus 1 will be a concave function. So now going to the actual idea behind the proof. So as I said, we have to break up this very large hive into small domains like this with 4 or 5 layer boundaries, which we fix. So if you want to understand what is the measure of functions close to a given hive, you want to get both a lower bound and an upper bound. So to get the lower bound, which is sometimes more delicate in our case, what you can do is you can essentially fix the values to the hive at these boundary values and say that I'll only allow these to fluctuate. Now, because these have got 4 to 5 layer boundaries, the pieces here do not interact. By do not interact, I mean there is no rhombus that both touches this part of the square and this part of the square, because this intermediate layer is so thick. And so the volume of the resulting polytope of all functions with these fixed boundaries is the product of the volumes of these polytopes corresponding to the pieces. So this is how we can get a lower bound on the volume, and similarly we can get a upper bound also with some additional arguments if you have an idea of what is the hive which is the most likely in some sense. So we'll come to that now. So before that, there is this issue of wanting to relate a term like this, which is in the continuous domain, but it is still discretized with these dyadic cubes, squares, I should say, not cubes, squares, or in some cases triangles, squares or triangles. This is all either square or triangle. Okay, so on this side you have an integral over the Hessian in the generalized sense. It's a measure, but you're looking at the measure of the Hessian over a cube and dividing it by the Lebesgue measure, taking sigma of that, multiplying with the Lebesgue measure of a square, adding up and taking exponential. Okay, on this side. On this side, you're simply taking the absolutely continuous part of the Hessian, taking with a minus sign, taking a sigma of that, integrating it with a minus sign, and taking exponential of that. The claim is these two are the same. Note that we need something like this because that whole process that we were doing, ultimately of breaking up into cubes and all, will get us only this far. But what we want to actually get a handle on is this. So if you want to get a handle on this, you better be able to prove that this has to be equal to this. So that is why we need something like this. And this is proved using submartingale convergence and uniform integrability. So these are some ideas from measure theory. Due to lack of time, I think I have to go a little fast. But let's see. So what is the idea here? So we are going to look at this sigma field generated by all possible events kappa, where kappa belongs to the set dA of dyadic triangles or dyadic squares of side length 2 to the minus a contained in T, kappa being half open. So this forms a partition. And we are basically looking at the following process. You pick a random point in the triangle, and then you look at the expected value of the Hessian integrated over its square at level 2 to the minus a. So you have this dyadic decomposition. You pick a random point. This is your underlying point somehow. And you look at a process where you keep on looking at the average Hessian as the square becomes smaller and smaller, always containing this point. This is some process for both the absolutely continuous part and the singular part. We have a similar process, singular part. Because sigma is convex, why is sigma convex? Sigma is convex because f is concave and sigma is the negative log of f. Why is f concave? F is concave because of Grunwald. So this implies that the expectation of sigma of x tilde a plus 1 plus y tilde a plus 1 given fa is greater or equal to sigma of xa tilde plus ya tilde by the convexity of sigma. And so sigma of xa plus ya is a submartingale. Similarly, sigma of xa tilde is also a submartingale for the same reason. So a collection of random variables xi, I belong to I are said to be uniformly integrable if the limit as m tends to infinity, sup I belongs to I, expectation of the absolute value of xi multiplied by the indicator of the absolute value of xi being greater than m is equal to 0. So this is the definition of uniformly integrable random variable. So indexed by a collection I. So there is this submartingale convergence theorem which says that the following are equivalent. A submartingale is uniformly integrable and it converges almost surely and in L1. So we're going to use this theorem to show that the random variable sigma of xa tilde plus ya tilde converges surely and in L1, almost surely and in L1 to sigma of x tilde. So that singular part doesn't matter. So what is the idea? The idea is that first you have to prove that it is uniformly integrable as a submartingale. So the logarithmic growth of minus sigma gives uniform integrability via a criterion of de la Valle Poisson, which basically says that there is some functional of these random variables, which if that function is convex and has the property that it divided by t tends to 0 as t tends to infinity, and then so there's some criterion, and then this thing is uniformly integrable, and if it is uniformly integrable, then together with an application of the Lebesgue differentiation theorem, which is required to show that ya tilde converges almost surely to 0. So ya tilde is this thing that is coming from the singular part of the Hessian. So what happens is it is somehow concentrated on a Lebesgue zero set. So because of that, when you take these cubes, they kind of, most of them will not contribute, most of them will not have a large contribution from ya tilde as a tends to infinity. So that's the idea. So all this converges almost surely to 0, which implies that the almost sure limit of sigma of xa tilde plus ya tilde is equal to sigma of x tilde, where in terms of the absolutely continuous part. But this says that it converges almost surely and in L1, and I think so. Some argument of this sort shows that it also converges in L1 to sigma of x tilde. So this fact that sigma is very slowly growing, logarithmically growing, this also plays a role. Okay, so next we are going to look at this upper bound. So how do we look at the upper bound? We are trying to get a upper bound on the contribution of a hive in one dyadic square. So the basic idea is that if you have a 4-layer boundary, use Brun-Minkowski to upper bound the volume of the relevant polytope as follows. So what we're essentially doing is we are saying, let's say you let's say you have fixed boundary conditions now. So you can fix the boundary condition by some union bound type trick. You basically there are so few nodes in the boundary of these things that you can kind of fix them up to some very high precision without paying in terms of entropy. So you can basically work with one setup where the boundaries are essentially fixed, and you get good upper bound and lower bound, and that's good enough. So for the upper bound, it goes via Brun-Minkowski, and there is this idea that if you have a set of values here which has an extension to the interior, which is rhombus concave, then you can subtract that extension, and now you get zero boundary condition with a subconcave, with a sub. I'm sorry. So the semi-concave constraint now. The semi-concave constraint is that it's coming from the fact that you subtracted a non-uniform Hessian concave function from everything, and so you now have a torus-like thing, except that those upper bounds that were constant in the periodic case are no longer constant now, because we have subtracted something that is not a paraboloid, and you have to get an upper bound on the volume of this. But this lemma says that actually the worst case is when it is a paraboloid. So you just assume it's a paraboloid and do it. And how do you get this lemma? This lemma is an application of Brun-Minkowski to translates of the polytope, basically. So you keep shifting you have this polytope, you know its volume is something. You first take lots of rigid body motions corresponding to translation to the torus. And then you take that bunch of bodies and you apply Brun-Minkowski to all of them, an average. And this is what you get. So once you get this, then the marginals of log concave density, the log concave as a consequence of Pekopa-Liebler inequality. And Fradolisi's theorem says that the value of a long concave density on Rn at its mean is at least e raised to minus n times the density at any other point. Okay. So this is telling you something about, suppose I have frozen the values at a quadratic boundary, right? So what I do is I take a torus and I have this semi-concave function. By symmetry, I know that the mean is going to be 0 for the semi-concave function with periodic boundary condition. But now I want to know, if I freeze the boundary to 0, how much have I reduced the overall entropy? And this is not obvious, but because 0 is the mean, and by Fradolisi's theorem, it tells you that actually you don't reduce the entropy by much, because e to the minus n is only the number of nodes in the boundary, which is an insignificant term if you look at the scale of the bulk, which is of order n squared node. So this tells us that basically you get a large entropy when you freeze at the expectation of the boundary. If you freeze to other boundary values, all bets are off. But at least for the expectation, we know what will happen, and you don't lose too much entropy. So this is how we get the lower bound. Along these lines, we get a large deviation principle for the hives. Okay, so this is the large deviation principle for hives. We actually only get it when lambda and mu are C1 for some technical reason, which I won't go into. But when lambda and mu are C1, we get large deviation principle for hives as well, of this form, same form as for the matrices. And there is some issue about, you should note that I said that all this stuff, that lower bound hinges on Fradolisi's theorem, which in turn requires C2-ness. And or at least so the way the C2-ness comes is that actually if you have C2 with a uniformly continuous Hessian, then locally they look like paraboloids because the locally continuous Hessian. And then things work out. But if you don't have that condition, this lower bound that we have doesn't work as of now. So this is why the large deviation principle right now is only for lambda and mu to be C1. Because in that case, we can actually take any arbitrary C0 hive and kind of massage it to make it a C2 hive with very similar properties, and then use the massaged version, the C2 hive, and get what we want. So this is what I wanted to say, more or less. I've just repeated the large deviation principle for random matrices. And I want to mention some open problems. So one open problem is to get rid of that C2 condition for the large deviation principle, which is there because of the limitations of our proofs. And the second is we would like a closed form expression for f of s, using which you would like to write down a PDE for the scaling limit of a random augmented hive with given boundary condition along the lines of one Kenyan prop, a variation principle for dominant tiling. Such a result would shed light on tiling, random matrices, and asymptotic representations. So thank you for your attention.